All right. Yeah, we'll worry about that later. Let's get started with today's material. Okay, yeah, it's going. Today's chapter all about fluid mechanics. Probably my favorite chapter for first semester. So starting off, what exactly is a fluid? This is something that's a little bit hard to get good intuition for, and frankly, the answer isn't very good. Anything that flows is a fluid. That's what a fluid is. So it feels kind of circular there. For the purposes of our class, we will pretty much only be considering two types of fluids. Either liquids in some sort of container, or this atmosphere. Now, it's very rare that we think about this atmosphere as actually being a fluid and something that you interact with. One of the things people typically don't give much thought to is a straw. If I've got some liquid right here, and I stick a straw in there to suck up the liquid, how on earth am I getting that water to move up that straw? What is causing that to happen?
Negative pressure.
What is it?
It's the pressure from the outside air that's pushing the water up through into the
Right, it's the outside atmosphere pushing down on it. So initially, when you have a straw, you have the atmosphere pushing down on the outside and the inside. When you stick the straw to your mouth and you suck on it, you're removing the atmosphere there, and so you're getting rid of the pressure, and so the water moves up the straw. You can only move up the straw as much as the atmosphere is pushing down on you. Right now, we are in a sea of atmosphere. We don't think about it, but it weighs, all the atmosphere on top of me right now weighs about as much as 10 meters of water. If I were to go down 10 meters into water, I've now doubled the amount of pressure on me.
Yeah.
You standing right here, feeling all this weight on top of you, would be the same thing as if I stuck you on the moon under 10 meters of water. Same amount of pressure. And so you have the weight of all that atmosphere up on top of you, and all that weight adds up to about 10 meters of water. What does that mean? That means, theoretically, the longest straw you could possibly make and drink the water is 10 meters.
Makes sense.
Because once you get it up 10 meters, say that this is 10 meters, now the pressure produced by the water is exactly equal to the pressure produced by the atmosphere. 10 meters of water weighs as much as however many miles of atmosphere we have right here.
Don't you have to worry about like the water boiling and stuff?
Huh?
Practically, don't you have to worry about the water boiling inside of the vacuum of the straw at that kind of length?
Kind of. It would a little bit change the density as it heated up, but not much. What really matters more is where you actually are on the surface of the Earth and how much atmosphere is under you, because that varies a lot between sea level and being on Mount Everest. But rough approximation, that's what it is. And so it's this atmosphere. Most people think that a vacuum is somehow a force. Vacuums aren't forces. Vacuums just remove pressures. People think a straw, you create the suction, which creates a vacuum, and the vacuum somehow pulls up on the water and makes it come up to you. And of course that makes zero sense, because you got the Earth here, you got the atmosphere around the Earth, and outside of that you got perfect vacuum of space. Why is it sucking off the atmosphere of the Earth?
Well, I thought that's just
because that's not how vacuums work. They're just where nothing is. And that's all they are. So, think about our atmosphere as a liquid or as a fluid, and then contain liquids we'll call fluids, and that's pretty much all we'll talk about this class. So, our first new definition, well, not really new, we've already been using it, but introduce it once again. This Greek letter rho looks kind of like a P. I'll always try to keep the top more rounded to help us differentiate it, because we're going to use P for pressure, unfortunately. And it is how much mass per unit volume you have. It's going to be measured in kilograms per cubic meter. Those will be its units. Good? Give you a sense for this. If I were to take 1 cubic meter of our room here, haul it off onto the moon and go weigh it, it would come out to about 1.2 kilograms.
Really?
To give you a comparison, the mass of 1 cubic meter of water would be 1,000 kilograms. So air is very light. All these atoms, you gather them all up and go haul them off and go weigh them, doesn't weigh very much. Give you just another comparison, concrete is roughly 2,000 kilograms per cubic meter. And then just for the fun of it, a neutron star is 10 to the 18 kilograms per cubic meter. Very heavy stuff.
Yeah.
Okay, so with those new definitions, let's just start out with some very simple examples. We're going to be inside of a room that is 4 meters by 5 meters on the floor and then 3 meters tall. With me?
Okay.
First thing we want to do is we want to calculate how much all the air in that room weighs. You haul all that air up in a bag, and you go stick it on a scale. What's the scale going to read? Oh, weightless bag. So let's calculate that first. So how do we calculate the weight of all the air in a room?
You times the volume by the weight.
We know its density. Its density is what? The density of air
Is 1.2.
is 1.2, but what does density give you?
Math 101.
It gives you kilograms per unit of volume. So if you take your kilograms per unit of volume and you multiply it by the volume, you get the mass. So that will give us the mass of our air.
Yeah.
Does that make sense?
Yep, that makes total sense.
And so now it's just a matter of plugging it in on the calculator. So the volume of our room is 4 meters by 5 meters by 3 meters, that's 60 meters, times 1.2 is just going to give us 72 kilograms.
So fair amount of weight.
72 kilograms, yeah, that would be, this room is probably pretty close comparable to that, 5 meters by 4 meters by 3 meters.
Why don't we feel any of this weight?
Why don't you feel any of the weight? Great question. I've got all that weight holding on me. Well, how can I say that? You do feel the weight, you feel it as pressure. You don't notice the weight. What's the difference between feel and notice? You experience all the physics of the pressure, is probably a better way to say it.
You'll feel the pressure if you sit there and hold your hand up like that for 3 years.
That's
The problem that you have is the pressure up on my hand right here and the pressure down on my hand right here are almost identical. And so it completely cancels out.
When your body is totally used to it.
It's like the difference between, imagine I stick you inside of a swimming pool full of water, and you stick out your arm. You don't really feel the water above you because all the water under you is kind of holding it up as well. You can kind of think about it like that. Now let's say I go put you out on the concrete, I put the swimming pool on top of you, and now I fill it up with water. That's going to crush you.
yeah.
Because now you're actually trying to hold up all the weight of the water, and you're not inside the fluid itself, letting the pressure of the fluid cancel it out for you. So there's kind of the two different scenarios. You want to be in the pool, not under the pool.
That makes sense.
Okay, anyway, so 72 kilograms. What would it have been if instead we filled it with water?
A lot more.
6,000.
Yeah, we got 60 here times 1,000 would be 60,000 kilograms. So, a lot more if we fill it with water, but still, 72 kilograms, that's not nothing.
Yeah.
Okay,
That's like what, 140 pounds?
something like that. So now, let's move on to pressure. Again, we've already talked about pressure, but reintroduce the definition. Pressure at a point is the little tiny bit of force being applied exactly at that point over the little tiny bit of area.
Right.
If you have a uniform force, and pressure is just force over area, here's what it is for a particular point, arbitrarily small area. Don't want to call it a point, want to call it a really small area.
Which is infinitesimally small.
Yeah. Arbitrarily.
Sure, not infinitesimally, arbitrarily.
Okay.
Okay, but really small. But here's what it is when the force is uniform. Then it's just force over area, which is what we've been using.
Right.
Important. Sorry. Pressure is a scalar, not a vector. Pressure always acts perpendicular to the area it's making contact with.
Okay, that makes sense.
If I fill up a pool, regardless of how wonky the edges of the pool are, here's my pool edges, and I fill it up with water, the pressure is always pushing exactly perpendicular to the edge of the container and to anything inside of it. Always exactly perpendicular.
Even upwards.
Yes, it's always exactly perpendicular to the surface. If it wasn't exactly perpendicular to the surface, if it was a little bit off, then that would create a force which would create motion in the water, and now the water would just be moving.
Yeah.
Create torque.
So, pressure is a scalar, not a vector. It is always perpendicular to the area of contact.
Why isn't it a vector that's just perpendicular to the area then?
Because we can talk about the pressure that this thing is experiencing at a point and now represent it perpendicular. But when we talk about the pressure in this room,
Oh, where do you do that?
then now it doesn't make sense to talk about this, right?
Right.
So, just a scalar. Okay. So pressure, force over area is the way you typically calculate it. We measure it in pascals, which are newtons per meter squared. Now, what is a newton?
It's the amount of force required to move a kilogram on 1 meter.
So if I were to take a 1 kilogram object, how much does it weigh
What?
in terms of newtons?
9.8.
9.8 newtons, basically 10 newtons. Take a tenth of a kilogram, and that's going to essentially give you 1 newton of weight.
Yeah.
So if I've got a force exerting a tenth of a kilogram of mass every square meter, that's almost nothing.
Yeah.
So a pascal is a very, 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 very small pressure. This is not a big pressure. Trying to give you some intuition for this.
Kilopascals, don't we?
Huh?
We use kilopascals a lot, don't we?
Well, pascals are the standard unit,
Right.
not kilopascals. You can use them, obviously, but
Okay.
pascals are what the standard unit is. I think kilograms is the only one where we do something like that, where it's the kilo version that's the standard.
Yeah, that's weird actually.
Anyways, so Pascal is newtons per square meters. Now, just to give you a couple intuitions for your more daily use, you're probably used to more like using PSI, pounds per square inch. So our atmosphere that we're feeling right now is roughly 14.7 pounds per square inch. So when I'm holding out my arm, every square inch of pressure is like 14.7 pounds. That's a lot of pressure.
Fair amount, yeah.
That just doesn't exist.
It just doesn't exist. It exists. Remember, being in the pool versus being under the pool. That weight is still there. It's just you got the weight of the water help, or you got the mass of the water helping you hold it up, you can kind of think about, versus not having the help. Now, in terms of pascals, 1 atmosphere is 1.013 times 10 to the 5 pascals.
Is that 10,000 pascals?
Basically 10,000 pascals. That's how much 1 atmosphere is.
That's quite a-
That's what we're experiencing right now. So a pascal is a very small unit.
Okay.
Okay? So when you're calculating pressures, you're going to get really big numbers. That's to be expected. Because you're going to be calculating mostly in pascals.
Okay.
Okay, so now let's go back to our room from example 1. Remember, the floor of the room was 4 meters by 5 meters. We'll pretend that that's this room right here. The question now is how much force is the atmosphere exerting on the floor right now?
How much is it weigh?
Sure.
Did we already do it?
No.
No.
70
This was
times G.
gathering up all the air molecules in the room, put them in a bag, go on the moon, put them on a scale and weigh it.
Why does it have to be big?
So that we're out of the fluid. It's really hard to weigh water in water.
Oh, so in a vacuum.
Sure. Yes.
Oh, I see why you're saying big, because there's gravity on it.
There's gravity on the moon so you can weigh it, and on top of that, there's no atmosphere, so it won't interfere with your weight.
So isn't that just 72 times 9.8? For the weight of the air in the room times gravity is the weight, is the force on the floor.
Well, let's see.
I hope so.
So, force on the floor in here. How do we calculate it? Pressure gives us force over area.
Oh, integrate.
I know the pressure. Remember, pressure is newtons per square meter.
Yeah.
If I have the pressure and I have the square meters,
You got the force?
you multiply the two together to get the force. You with me?
Yeah.
Pressure is how many newtons per square meter. If I multiply it by how many square meters I have, it gives me the newtons, the force. Or in other words, just move the A over here, and P times A gives you the force.
Yeah.
However you want to think about it. So let's calculate that. So our force now is going to be our floor's area times the pressure.
20 times
What's our area?
20 meters.
20. What's our pressure?
1.0.
The atmosphere. And so you're going to get 20 times 10 to the, we'll say 2 times 10 to the 6 newtons. Okay, that is a lot more than taking that and multiplying it by 9.8.
Yes, how does that work?
How does that work? What is producing that pressure on the floor right now.
Oh, it's the weight.
It's the weight of the entire atmosphere. For the way you want to do it, what we gotta do is, here's the Earth. We gotta take, here's our room right here. Take all the air in a tower all the way up to the top of the atmosphere, weigh all that, multiply it by 9.8, or get its mass, multiply it by 9.8, and then we get this number.
Oh, okay.
So it's the weight of the entire atmosphere on you. And so this floor right now is holding up a force of 2 million newtons.
Oh, this young.
I think that came out to like 250 tons or whatever.
Okay.
Wow.
How's the floor holding up all that weight?
Because there's air underneath.
Because there's air underneath the floor too that's helping hold it up. Fortunately, the floor's in the fluid.
Well, something's holding it all up. Which would be Earth, right?
Yeah, something's holding it all up. So the Earth is very compressed.
And that's the one, yeah, the Earth has to do with way more than just the air.
Yeah, the Earth has to do a lot more than just hold up the air. It has to hold up all the weight of the Earth all the way down. And pressures get insane when you get close to the center of the Earth. It's a lot of weight. But so even there, huge difference. Weight of all the air in the room, pressure in the room, the force due to pressure in the room.
That's so weird.
And so when you think about, this is also equivalent to going 10 meters underwater. If I were to take some submarine now, build it out of materials, and make sure that submarine had the exact same surface area as 20 meter surface area, and stick it underwater 10 meters, it now needs to be able to hold up 2 times 10 to the 6 newtons in order to withstand that pressure.
That's crazy.
Submarines are not easy to build.
That's
Don't humans,
The first submarine, I think the guy was able to get like 5 meters deep.
don't humans swim deeper
Don't humans swim. Humans do swim.
deeper than that?
And so when you swim in the fluid,
Oh, that's-
you are in the fluid. And you're not trying to hold the fluid out, you're in the water.
your body has to.
Now, what you still need to do, even when you're swimming, is you need to breathe. Right?
It's a big problem.
And so, if you were to try and go snorkeling, and try and build yourself a little tube to go snorkeling, about how far could you go down in the water and still snorkel?
Meter tops.
Maybe like a meter tops, if you're a really good breather. That's some tough lungs.
Scuba diving, even the pressure stops you from inhaling at some point.
Scuba diving, they have to use pressurized air tanks that they breathe out of,
Yeah.
that are pressurized to whatever depth they're going to,
Oh,
so that the pressure inside their lungs is the same as the pressure out in the water.
so they breathe more dense air.
So they breathe much more dense air
They need to breathe.
It's still
If-
to keep their lungs inflated, otherwise it collapses.
the deepest you can go is
Mythbusters did a,
100 meters.
100 meters before. Well, that's.
what are those underwater old-timer suits that people would use to walk in water? You know, the big
Oh.
wetsuits with the big metal helmet.
Yeah.
So one of the episodes of Mythbusters came from a story where there was a guy, you know, he's wearing one of those big suits, big helmet thing, and then he's got his body, and he's, you know, walking the ocean floor, big helmet on. These things have an air, they have an air thing all the way to the top, feeding them pressurized air. The air pressure got cut off to one of these guys, which forced his entire body up into the helmet,
Yeah.
crushing him.
Kill them.
Kill him, yes, as he was very dead. Suddenly taking on all that pressure in an instant,
Did
being
he know
crushed up
this
into the
would
helmet.
happen?
Well, no, you
No, there was a mistake in the system that caused it to go off, or something like that. I don't know, there's an episode of Mythbusters on it, you can go watch it, but.
If it's condensed air, wouldn't the oxygen be more connected to? And your brain can't take that much.
Sure.
What's he gonna do with 5
I'm not sure what happens ratio-wise in terms of maintaining things, because it's not so much how much oxygen you have as air pressure.
Yeah.
Well,
So
there's
maybe
much
it's pressurized, but with a lower concentration of oxygen, make it the same. I have no idea.
I see what you're saying.
But the world record for scuba diving is about 120 meters.
Okay, so we did that. Now introduce us to Pascal's law. Pascal's law says pressure applied to an enclosed fluid is transmitted to every portion of the fluid and the containing walls undiminished. Containing walls of the fluid. So the pressure, if you increase the pressure on a fluid in one place, you increase it everywhere. You can't increase the pressure on one part of the fluid and not the rest of the fluid. Doesn't work.
Okay.
Oh, because it kind of moves out of the way.
So it's transmitted undiminished throughout the entire fluid and to the containers holding the fluid together. Good?
Is this fluid like a liquid fluid or
Liquid fluid, gas fluid,
both?
both. I can't increase the pressure of the room over there and not increase the pressure over here.
You
Kind of can, but can't.
Not really.
That's how
It's going to spread. It's kind of like trying to increase the temperature in one part of the room without it affecting another part of the room.
So you have to. That's just assuming that they're not different rooms, like not different. Not
Right, all fluid in the same container.
Is our atmosphere in a container?
Close enough. For the purposes of this, sure. I mean, once you go far enough differences, now you can get pressure differences
Right.
that come and go with like weather and stuff. But for the most part, yeah. For the purposes of what we talked about, yeah, we'll always be talking about like in a room or something like that.
So what's air turbulence?
We will not be saying anything about turbulence, and we will not be saying anything about vortexes in this class.
At all?
Adds way too much complexity.
That sucks.
Can we get a rundown sometime?
You can read the quick summary that your book gives you. Okay, continuing with this, or maybe at the end of class we can talk about. Let's see now how pressure is related to depth. Obviously, the deeper you are, the more pressure you experience. So let's come up with an equation that relates our pressure and our depth. So here I've got some big swimming pool or some fluid in a container. I am taking just some arbitrary slice of it. So this isn't something in the fluid. I'm just saying let's focus on the fluid right here in this rectangular part. With me so far?
Yeah.
All right, so there's nothing in the fluid, just a fluid. And drawing up a free body diagram. So we're taking an arbitrarily thin slice because we are going to assume that pressure is related to depth. And so the pressure all along the slice is going to be roughly the same.
Yeah.
Because it's an arbitrarily small depth.
Well,
Slice.
sorry, we'll have a different pressure at the top and the bottom, but I'm saying for a slice, even through that, we're going to assume it's uniform.
Yeah.
So at the top, we'll say that the pressure, well, we'll start from the bottom. So the pressure on the bottom is just going to be, sorry, the force on the bottom is going to be P times A. Whatever the pressure is there times A. That's the force on the bottom, drawing a free body diagram. For this little infinitesimal bit of the fluid, it's got some weight, dW, pulling it down, pressure pushing it up. On top of that, we're guessing is going to be a slightly different pressure because you're at a slightly different height. So the pressure there is going to be P plus dP, some small change in the pressure, maybe positive, maybe negative. In this case, dP would be a negative number.
Yeah.
So you could switch those orders if you want.
Times A. Yeah, I could have called this the P plus dP and this the P. I'm going through the standard way that's derived because we're going to call this the up direction.
Interesting. Okay.
Oh, that makes sense.
So X direction, Y direction. In the X direction, we expect that the pressure pushing on this side is exactly equal and opposite to the pressure on that side. Or sorry, the forces from the pressures. Those cancel out. So all we care about is in the Y direction, what's going on.
Yeah.
So we are assuming that we are in an equilibrium state. We're not talking about the water moving. So you come across some pool, and you're looking now at this little bit of water in the pool. So it's not moving, everything's still. If everything's still, and it's in equilibrium, then that means that, drawing up the free body diagram, the forces have to perfectly cancel out. So however hard P times A is pushing up, this pressure plus this weight are pushing down, equal and opposite. So that overall that water is not moving, it's just holding still. Following me?
Yeah.
Yeah.
So P times A is equal to P plus dP times A plus dW.
Okay.
Follow our setup? That's your forces in the Y direction, that's all we care about.
And what are we solving for?
We are just coming up with an expression that relates pressure with your depth. We're trying to relate pressure and Y here.
Okay.
Good? Okay, now dW, that's the infinitesimal weight of that water. What is its infinitesimal weight? It's going to be its infinitesimal mass times G. Remember, density times volume gives you mass times G gives you weight.
Okay.
So rho here, that's the density of whatever the liquid is that we're talking about. And dV is the volume of that arbitrarily small slice that we took.
Okay.
Good so far?
Yeah.
Okay. Now what is dV? It's just going to be whatever the area is times dy, the height. So that's my only substitution going from here to here and a little bit of reordering.
Right.
With me so far?
Yep.
Okay. So now, that's just noticing what dW is. So back to this equation, we're going to substitute in the dW.
Okay.
So from here to here, just a dW. So that's the same. This, I did the distribution, but still the exact same thing. And then here's our dW. Good?
Okay.
Okay. So now,
We factor out A.
factor out an A. No, I think all of our subtract a PA from both sides. So this cancels with that. You see that?
PA cancels with A.
Yeah.
Pressure times area and pressure times area showed up on both sides.
Oh, so you,
Subtract to both.
Yeah.
And I'm going to move this one. Well, I'm going to keep this one on this side, move this one to the other side. So it's going to be negative. So this one goes to the other side, becomes negative. This one stays on this side, and I swap the sides I'm writing on. So those two terms went out. So this term is equal to the negative of that term. Good? Okay. Now I can divide the area out from both. Could have done that to begin with, but now I'll divide it out. So cross out the area, and I get your change in pressure is equal to the negative of your density times G times your change in height. In other words, if you change your height so that you're going up out of the pool, your pressure gets smaller.
but pressure changes every time you move then.
Yeah, as you go up, your pressure gets smaller and smaller and smaller. And as you go down, your pressure gets bigger and bigger and bigger. Or in other words, your change in pressure with respect to your height is equal to negative rho times G. The density of the material times G. So, let's make intuitive sense of that. This means that a denser fluid produces more pressure, and more gravity produces more pressure, which we would expect, right? Okay. So there is our relationship between pressure and your location. Good so far? Okay, so now let's analyze a change in pressure going from one point at this depth to point 2 at this depth. So here's 1 point, here's point 2. What is a change in pressure? That's what we're looking for. So to get our change in pressure, we're going to take dP here. We're just taking this equation and we're going to integrate both sides.
Okay.
To tell us how it goes from here to here.
Right.
So we're going to integrate from point 1 to point 2, the pressure,
Yeah.
which will give us a change in pressure. That will just be your ending pressure minus your initial pressure.
Okay.
Hopefully that's straightforward calculus, remembering what's the integral of dx? X. What's the integral of dP? P, evaluated from here to here. Good. Over here, we are assuming that rho is a constant,
And G's.
meaning the density of our fluid is not changing, and that G is a constant, meaning we're not changing such drastic heights that the pull of gravity is changing. With those two being the case, all this becomes a constant, and now it's just the integral of dy. What's the integral of dy?
Y.
Y. And now evaluate from y2 to y1, or from y1 to y2 gives us y2 minus y1. So that gives us this equation.
Yeah.
So your change in pressure is equal to rho g times your change in height. And it's going to be the negative of them, meaning if pressure is increasing, then your height,
Decreases.
if your height is increasing, if you're getting higher out of the water, your pressure is decreasing.
Yeah.
Okay. So that's what that negative sign is doing. Good? Okay. Now, how we typically want to think about this, just a special case of that equation, typically the way that we want to think about this isn't the change in pressure between two random points. We want to say if the pressure is one value at the top, what's the pressure if I go down some distance h? That's typically how we want to think about it, is how pressure increases as we go down, not as we go up.
Right.
Yeah.
So-
increases.
We're going to do one more example now. So we're going to have P naught is your initial pressure at the top of the fluid. We're going to calculate your pressure if you go down some distance h. With me? And we're just going to substitute directly into this equation. Our pressure at the bottom is what we're going to call P2 in that equation. Our pressure at the top is what we're going to call P1. H now is going to be Y1 minus Y2. Because that's what we're saying we want to care about now. We want to count how far you went down this way, not how far you went that way.
Okay.
So y1 minus y2, which is negative y2 minus y1. So negative y2 minus y1, those together are going to be h.
Okay.
So this will be p, this will be p naught. The negative and y2 minus y1 will all be h, and then the rho and g will still be there. So here it is. And here's what you'll likely use most frequently. Actually, one more, put the initial pressure on the other side, and here's how you'll typically do it. What's your pressure at some new point is equal to your initial point plus rho times g times how much further down you went.
That's really simple.
H.
Yeah, but your rho changes so much.
No.
Rho is going to be the density of the fluid. The density of water does not change. You can't compress water to make it more dense.
Pressure changes though.
Pressure changes. Okay,
So it's your
that is rho. This one is rho. That is a constant for the material.
Okay.
That is 1,000 kilograms per cubic meter if we're talking about water. It's the constant for the material. It's how dense that is. This is 1.2 kilograms per cubic meter if we're talking about air.
You're saying the density of water doesn't change whether you're 1,000 meters deep in water versus you're at the top.
The change in density is almost impossible to measure.
Really simple.
It is very hard to compress water anymore.
But it's still, then what does a black hole do? It compresses things,
Well,
doesn't it?
okay.
Yes, a black hole can compress water. The ocean cannot compress water. And water at the bottom of the ocean is not more compressed than water at the top of the
It's
ocean.
not more compact.
No. It's pretty much as compact as it comes. I mean, slightly in a way that you could hardly even measure. Yes.
That's why hydraulics work.
So it's all just pressure.
Yes.
So it's all just pressure.
There's not a change in density.
It's not more condensed. It's not more dense. It's just pressure.
There's not more atoms in the same area.
I know that doesn't make sense. It feels like it would be way more compact.
It's already as scrunched together as you can get. There's no more space to squeeze out of it.
From the top and the bottom, basically.
From the water. When you got a cup full of water, and if you were to hook up some sort of system to try and compress that, you're not going to be able to compress it anymore.
A black hole could.
A black hole could, you're not going to be able to. And no device that Newton knew of in his day could do it. And we're going to do Newtonian mechanics.
What
Can
about,
we do it now?
what about like solid stuff? Like what about turning the liquids into a more condensed solid? Like you know how solids are usually denser?
Yes. So water's weird because it doesn't do that.
But other fluids, that is the case, right?
Other fluids, that is the case. Water is not one of those. Water is uncompressible. For the purposes of our class, liquids are not compressible.
Don't we have a bomb that uses compressed water?
Okay.
A bomb that uses compressed
So now let's move on to our next topic, a hydraulic lift. What is a hydraulic lift? Here's the idea. So I've got this container, it has a big open area over here, small open area over here, and there's some fluid in there.
Okay.
Oh, wait. You're using the weight.
What do? I hook up a piston right here so that no water can escape, and I exert a force F down on that piston. This also has a piston on it so that no water can escape and it can't move up.
Well, then it just.
Because the water cannot compress, it is not compressible, and because of Pascal's law over here, whatever pressure I produce by pushing down on this piston has to be reproduced on this piston over here.
Right.
That's Pascal's law.
But all the water to each other are increasing pressure too.
Yeah, the pressure goes all the way through, pressure increases as I push down, but the point is, I push down producing a pressure right here, a point the same height has the exact same pressure.
Yeah.
Now, how do we calculate pressure? Well, force over area. So, if I'm producing a force F1, and this has a cross-sectional area A1, so F1 over that area, it will produce a resulting force over here of F2 over A2.
Mm-hmm.
Where F2, so these two are equal to each other, now solve for F2. F2 is equal to A2 over A1 times F1. What does that mean? If this area of this piston is 100 times bigger than the area of this piston, then me pushing down on this piston with the force of 10 newtons produces a force of 1,000 newtons pushing up over there.
If you can manage to do that, but
I can push down with 10 newtons so easy, it's ridiculous.
isn't the kickback 1,000 newtons though? 10,000 newtons on you?
Now,
How does that work?
the pressure can't change. If that were a pushback of 1,000 newtons on me over that area, that's a massive pressure. The pressure is a constant. The pressure here and the pressure here are the exact same. What is pressure?
Yeah. but
Force
you
over
can't-
area.
You can't just push it down and.
Yes, you can. This is exactly how a hydraulic lift works.
you're
You've got
shooting-
this piston, and what do? You push it down some, which causes this to raise some. And then you have the system set up so as you pull it back up, water is allowed to flow in but can't flow out of the system. So some water feeding in right here, it's a valve that only lets go one way. And then you push down again, which pushes this up some. And it's how you raise a car on a platform. And you can be sitting there with your little hand chugging away, slowly pushing up more and more and more and more and more.
That doesn't make sense because you're getting something out of nothing.
Now you're not getting something out of nothing. You say, doesn't this break conservation of energy? And the answer is no, because however much volume I push down here is how much volume I push to over here.
So you're pushing that a lot smaller.
So it's a small volume. So let's say that I push this down some distance d1. And how much does that lift it over here?
A very
Very
small.
small.
Very small amount. Well, let's actually calculate it. What's the volume that I compressed over here? The volume that I compressed over here was equal to the area, A1, times however much I compressed it, D1, downwards. Right? Now, that has to be equal to the amount of volume of water that moved over here, because water can't compress any. So that has to be equal to A2 times D2. Or in other words, solving for D2 is going to be equal to what? A1 over A2 times D1.
Pretty similar to what that was.
So, if A2 is 100 times bigger than A1, then D1 is 100 times, or D2 is 100 times smaller than D1.
That's still cheating it.
So, if I want to raise this 1 centimeter, I have to push this down an entire meter. And what is work? It's force times distance. So F1 times D1 will still equal to F2 times D2. Over here, I'll produce a massive force with a really small distance. Over here, I'll produce a really small force with a really big distance.
And so your work is zero.
It's kind of like the difference between gradually sliding a box up a frictionless ramp versus trying to just pick it up and go in one go. When I slide it up a frictionless ramp, I have to move it way, way further, but I can use a smaller force to slide it up. Whereas if I try to just lift it on the table, I have to do a way bigger force, but a smaller distance.
The distance is
Yeah. What?
Sliding a box all the way up a ramp
versus going straight up to get up.
versus lifting it. It's a way bigger difference.
Yeah.
To get up, though, not.
Yes. not-
Right. So we do not cheat. We do not get something for nothing. Energy is still conserved.
Interesting.
You want to apply 1/100th the force, you're going to have to use 100 times the distance. So physics works. Can't break it.
Still. A little fishy, but
All right, come up with a way to break it.
black hole.
Okay, so that's a hydraulic lift, something that are used in, well, all over the place, but like a garage or whatever, where they're doing mechanical work, lifting a carp in the air.
Or
Do they use
tractor.
hydraulics for tractors?
Yes. They just like a tractor.
So how does that work? Is it-
Similar concept. We're not going to get into the mechanics of a particular device. We're focused on the physics. Okay, so let's move on to our next topic now, which is absolute pressure versus gauge pressure. Here you have a car that you're driving down the road and the tire popped, and it's a flat tire. What is the pressure inside that tire?
It's 1 atmosphere.
It's 1 atmosphere. But if I hook up my pressure gauge and try to measure it, what does it say? 0 psi. It does not tell me that I have 14.7 psi in my flat tire. It tells me I have 0 psi in my flat tire. Because a gauge tells you the difference in pressure between what's in the tire and what's in your atmosphere.
So it's just set to 14 psi.
Well, that's all it measures is the difference in pressure. And so all it says is the difference in pressure between your tire and the atmosphere is 0. So gauge pressure is what the gauge would tell you. Absolute pressure is the actual absolute pressure. So typically, how do you get absolute pressure from gauge pressure? You just add 1 atmosphere to it. Typically.
Okay.
Make sense? Okay. So with that, let's quickly calculate the absolute pressure versus the gauge pressure at the bottom of a 12-meter tank of water. So here I've got some big tank of water, 12 meters deep. I come and I measure the pressure right here. So what's the pressure going to be?
The most it's ever.
The pressure is equal to the initial pressure, whatever it was up here, P naught,
Which is an atmosphere, right?
plus the density of the material, rho times G times H, however far down we are. If we're going to talk about atmospheric pressure, or if we're going to talk about absolute pressure, then I would use the pressure of the atmosphere for P naught.
Right.
If I were just talking about gauge pressure, then I would use 0 for P naught.
Okay. That makes sense.
Yeah.
And so we'll just calculate one of the numbers, and then who cares about the other one? All right, so P then will equal, let's do the absolute pressure. So it's going to be 1 atm, or in other words, it's going to be 1.013 times 10 to the 5 pascals plus rho times G times H. Pull out our calculator. And now I told you that under 10 meters of water is roughly 1 more atmosphere. So this should be roughly more than 2 atmospheres. So it should be a little bit over double this number.
Yeah.
So there's our sanity check to make sure we're not making a mistake. But 1.013 times 10 to the 5 plus, what's our rho?
1,000.
1,000
9.8.
times 9.8 times 12. And it comes out to,
800.
Yeah.
let's see, I got 1.13 times 10 to the 5. What did I do wrong?
Yeah, what?
Where you-
I did 100 for waters, rho, not 1,000.
Well, when-
Okay, there we go. It's 2.19 times 10 to the 5 pascals. There we go.
Would it just be a factor of 0?
So, should have been roughly double that number, which is exactly what it was. This is roughly 1 times 10 to the 5. This is roughly 2 times 10 to the 5, a little bit more. So that's what we expected. If we wanted the gauge pressure, just don't use that term, and there's gauge pressure. Okay, boring stuff. Let's do something a little bit more interesting. So our next example, we've got this glass tube open to the atmosphere on both ends.
Okay.
Okay.
So 1 atmosphere pressure at both ends here. We put water and oil, we slowly pour them in, keeping the middle right smack there, and get them as full as both of them can be. Oil is a little bit less dense than water, so it's going to be able to go up a little bit higher.
It's going to be pushed.
So it's pushing the same amount as the water. Now, I think that they wanted us to come up with an expression for the height of the oil as a function of the density of the two materials and the height of the water. But it makes sense that the height of the oil should be a little bit taller, right?
Yeah.
Okay, now, since these two things at the bottom, we kept the fluids the same, the pressure there, P, is the same for both materials. If I were a teeny bit on the water side, my pressure would be P. Teeny bit on the oil side, my pressure would be P. Make sense? Okay, and what is the pressure there?
Pressure is equal to the
Your
initial
P naught plus your
minus
rho times G times H.
Right? Now, I can't remember if they wanted absolute pressure or gauge pressure. What example is this?
by
3
absolute.
is 4.
Example 4.
Just they want absolute.
It says 4.
Meter is filled, blah, 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 blah. Find the relationship between the heights, H of oil, H of water. So it doesn't say anything about either of those. So, oh well, we'll keep going. So this we'll say is for the water side. So this will be rho of water, and this will be H of water.
Why are we finding two pressures?
Okay, what is the pressure here? It's P. Now imagine that instead of having the oil here, my container ended right there, and we didn't have any oil at all. Does that change the pressure there? No.
So you could do oil.
So considering just the water half, here's my pressure. Considering just, oh sorry, that's a P naught, not a P of oil. Okay.
Yeah.
And then if we consider just the oil side, once again, that's going to be P naught plus our rho for oil times G times the height of the oil. With me?
And those P have to be the same.
Those have to be the same, so those are equal to each other. So I know that P naught plus rho of water times G times the height of the water has to be equal to P naught times the rho of the oil times G times the height of the oil.
You're using Newton's law.
Sorry, plus. Subtract P naught from both sides, divide both sides by G, and what do I get? I get that the rho of the water times the height of the water is equal to the rho of the oil times the height of the oil. Or if I wanted to solve for just the height of the oil, I could write it as the height of the oil is equal to, just moving that to the other side, rho of water divided by rho of oil times the height of the water.
You're trying to find height.
The height of the oil with respect to the height of the water. And it just depends upon the ratio of their densities. Now it doesn't really matter that this is water and oil, it could have been any two liquids you wanted, and this will tell you the ratio of the two heights. Notice, what does it tell you if I use water and water on both sides?
The height of the water is equal to the height of the water.
Then the height of the water would be the height of the water, because this would just be 1, which is what we expect.
Yeah.
And if we had a material that was 1,000 times denser, then it would be 1,000 times more
More. Yes.
in the height.
Right.
Now, what do I have? Oh no, I was just thinking about that.
So why
If it's 1,000 times denser, it has 1,000th the height.
Yeah.
Okay.
Why do you set them equal to each other?
Because the pressure here from the water is the same as the pressure from the oil.
Yeah.
So the pressure is the pressure.
We just solve it.
And so here's the pressure for the water, here's the pressure for the oil, it's the exact same pressure. So those are equal to each other.
You use height when you.
Oh. Yeah. Okay. I see.
So we just solve for that. It's pressure.
Good? Making sense? Okay. Let's move on now to buoyancy. Has to do with objects floating. Let's see. What's the common question?
Why does ships float?
Why do ships float?
Isn't that pressure?
Yeah, it's buoyancy. But here's the common scenario. Here I am, I'm in a pool of water, and in that pool of water, I'm in a canoe.
In the pool?
Yeah, in the pool, I'm in a canoe.
Okay.
The height of the water is perfectly measured. Inside the canoe, I'm also happen to be standing here, holding a solid bowling ball. So no empty space inside the bowling ball. There's my solid bowling ball. So I'm holding the bowling ball, I'm in the canoe's in the pool, someone carefully measures it, all perfect like, and then I drop the bowling ball over the side, wait for everything to settle again.
This should be lower.
Did the water pressure go up, go down, or stay the same?
It should go lower.
Lower, the same?
Wait.
My guess.
Pressure.
My guess is lower because you have this water being displaced because the weight of the bowling balls on like are pushing
The
down.
pressure increases because of your rho.
Pressure, we're talking about the height of the water in the pool.
Oh.
Does it go up, go down, or stay the same?
Oh, I think
It
that's
stays the same,
It
right?
stays the same.
Stays the same.
It does?
Yes.
Now, it's going to go down if you drop the bowling ball over
No,
the
it
side.
doesn't. It stays the same.
Now, it's going to go down.
It
And
stays
so,
the same.
we'll make that make sense once we cover buoyancy and Archimedes' principle. So,
The bowling ball.
let's cover buoyancy. What is buoyancy? Buoyancy is what makes objects float, right? If I were to give you a beach ball and say, go stick this underneath the water, good luck. You're not getting it down there. The water's going to keep forcing that thing right back up.
Yeah.
That force, forcing it right back up, is what we call buoyancy. So how does buoyancy work? Once again, here we got a pool, and here we got some water in the pool. There's nothing else in the pool. It's a completely empty pool with just water.
Okay.
We're looking at this water right here in some random section of the pool. Who cares? There it is. That's the water we're looking at. And we're going to draw the free body diagram for that water.
Okay.
Now the water's completely holding still. Yeah, it's in equilibrium. We're not looking at water spinning in the pool or anything like that. Everything's holding still. Let's draw a free body diagram for that water. Now, it's got some forces pressing on the side, but those are going to be perfectly canceled out by other forces on this side. We're going to have a force F1 pressing down on it. That's like the weight of the water above it, or pressure due to water at the top. And we're going to have a force also pressing up on it from the bottom. And then finally, we have the weight of the water. If this is in equilibrium, then that water is not moving. So in the y direction, the force on the bottom is perfectly canceling out the force on the top together with the weight of the water. So the force F2 is equal to F1 plus whatever that weight is. Or in other words, the difference in the forces is whatever the weight of the water is. Does that make sense?
Yeah, it makes
The
sense.
difference in the forces here is exactly what we mean by the buoyant force. It's the difference between how much the water on the top of you and on the bottom of you is pushing on you. And it turns out it pushes on you with a force directly equal to the weight of the water that would have been there. Because now imagine that I suddenly replace that water with some object, some peanut-shaped object there. The water doesn't suddenly start pushing on it in a different way. The only thing I changed was its weight. F1 is still whatever F1 was, and F2 is still whatever F2 was. It doesn't actually care what was right there. So for any object with that shape, it will be pushed upwards with exactly this force.
The weight changes, doesn't it? If
The weight changes, yes.
a peanut versus
But F2 minus F1 does not change.
it F1 adapts to whatever weight is.
No. The pressure that is being exerted on this water, the pressure being exerted on this doesn't know what that object is. It doesn't look and say, let's see, what are you? Oh, you're water? I'm going to push this hard. Oh, wait, that's concrete? I changed my mind.
I mean F2. F2 adapts to whatever it pulls up
Well,
depending.
he's saying that F2 counteracts the weight of the object.
Yeah, so it changes depending on how.
Oh,
it
no,
is.
no.
No. F2 is just how much the water is pressing up on the bottom of the object.
I know the more.
It doesn't say, if you put a heavier object there, okay, now I need to push you harder. It says, no, you're going to start sinking because I can't hold you up. If it's just water, it's going to just sit there.
So F1.
If it's heavier than water, it's going to fall. If it's lighter than water, it's going to go up.
F1 and F2 are the same thing then.
No, the
What's
force at the top and the force at the bottom are a result of pressures. The deeper you are, the more the pressure can be.
Yeah. Okay.
F2 will be bigger than F1.
Because of okay.
If there wasn't that difference, nothing would float.
So weight
So
doesn't
things
matter.
float way, way easier at the bottom of the ocean than they do at the top.
No, because it's the difference that matters.
How big something is.
So if you have a really big object, it would float easier at the bottom of the ocean than at the top.
What matters is going to be the volume. It matters the weight of the water being displaced. Because this perfectly counters out the volume of the water displaced, the weight of the water displaced. That's what it cancels out.
Okay.
So with water, it will hold still. If you pick something heavier than water,
It'll sink or.
it'll sink. If you pick something lighter than water, it will move up. And that's what we call floating.
Yeah.
So it's from this buoyant force.
Strange.
So that's what we call our buoyant force. So the force of buoyancy is going to be the mass of the fluid you removed times G. Because that's exactly what W is here. It's the mass of the fluid times G.
Yeah.
So that's your buoyant force.
Wait, is that a vector?
Now, well, it's always upwards.
Always upwards.
Yeah, it's always opposing whatever the direction of weight is. So yeah, it's a force.
Vector.
Yeah, so it's going to be a vector. It's going to be a force.
Okay.
Good? Now, the mass of your fluid, you can always calculate as the density of your fluid times whatever the volume is.
Yeah, that makes sense.
And so that's typically how you calculate your buoyant force.
Can we do an example?
Yes. Before we do an example, we will now talk about Archimedes' law. So, here's Archimedes' law. When a body is immersed in a fluid, then the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So we're saying the buoyant force is always equal to the weight of the fluid displaced by the body.
Wasn't Archimedes the guy that had the whole
Eureka thing.
Eureka moment with the displacement in the bathtub?
Yes. So what led Archimedes to make this discovery, supposedly? He was charged with trying to figure out if a crown that a king had made was actually solid gold, or if he'd been cheated. Because sometimes if you give someone some gold and say make some jewelry out of this, they might use something like metal, some different metal on the inside, and then gold on the outside, and keep the other gold. So the king needed Archimedes to come up with a way to determine if the gold crown was solid gold. Now, Archimedes knows the density of gold, and so he could do its weight divided by its volume and figure out its density. But the problem is, how do you find the volume of a crown?
Pretty hard.
He didn't know how to do that. So, what he realized, supposedly, is getting in his tub was filled to the brim. When he got in his tub and sat in the water washed out. And he realized exactly as much water just went out of this tub as the volume I put in the tub. And so how can you get the volume of a crown?
Put it in the water.
Fill up the tub, drop it in, and it will displace as much as is equal to that crown. Now that's one way to get the volume. That's kind of annoying because you got to collect all the water to go measure it. Really, the way you would do it is you would look at the weight of the crown, and then you would look at the weight of the crown in water and compare the two.
What does that give you?
It gives you the density of the material. So we'll do something kind of like that now. An example. Here's our example. We are going to calculate the tension in a rope in some salt water holding up a gold statue. So I've got a gold statue here. I've got a cable, a weightless ideal cable holding it up. So it's exerting some sort of tension here, T. I've got the weight of the statue pulling it down, W. And I've got the force of buoyancy.
So it's in water.
Yeah, it's immersed in water. Here we are in the ocean.
In and out of water. Oh,
No.
So here you are in your boat, and you're fishing for a gold statue.
okay.
Boop, boop. All right, there you are. Very happy guy. Here's your gold statue. Force of buoyancy, which way is it pushing?
Up.
Up. And so our job now is to come up with the tension inside of here.
Is this in equilibrium?
It's in equilibrium. Right now it's completely holding still, not accelerating upwards or downwards.
Meaning it weighs the same as water. Or its density is the same as water.
Now, and no. It's a gold statue. Its density is the same as gold. The density of gold, I think I scribbled it up here somewhere.
Meaning the tension.
Did I erase it thinking it was part of another problem?
Quite likely, yeah.
Yeah, that's possible.
Yeah, row of gold is, I want to say 19.6 times 10 to the 3. So roughly 19 times as dense as
Water?
water. Gold, 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 19.3. Okay. Wow, I said 19.6. Okay, so there's the density of gold. 1 cubic meter of gold would have a mass of 19,000 kilograms.
So why isn't it sinking or rising?
We're hooking it up to this fishing pole, and so we're holding up some of the weight. Look, gold's way heavier than water. If you took a gold statue into the ocean and let go, it's not going to float.
It goes straight
It's going to fall to the bottom because the weight is way more than the buoyancy force.
Oh, so ships float because they weigh less than the water that they displace?
Correct. Well, they weigh exactly as much as the water they displace. Oh, well, they displace as much water as they weigh and are still above water.
And so
The submerged portion of the boat is equal to how much water it displaced.
So objects don't float because they don't displace as much water as they weigh.
Objects float because their volume, their density is less than water when you calculate with their whole volume.
So just density.
It's all about density. So I can make a boat out of steel, that's no problem. Steel would normally sink, but then I have a hollow on the inside. And now I'm standing on the inside of my steel boat. And so, the steel, if I were to melt it down into just a bar, then it would sink. But since it's hollow on the inside and it's, it's submerged in water that much, the volume that it displaces
It's less dense than the water that is.
weighs as much as my boat.
Gotcha. Because it's less dense.
Because my boat overall is less dense, even though the actual shell of the boat is made out of steel, which is way heavier.
That makes sense.
And so, a steel boat can float just fine. You just need enough air, enough empty space.
That's cool.
Make sense?
We'll get there.
So, that's the force of buoyancy. Anyways, here we are, and we're fishing for our gold statue.
Yeah.
Okay, we're in equilibrium. Let's draw our free body, or here's our free body diagram. Let's look at what's in play here. We have downwards is the weight. Well, I think we're solving for tension.
Yes.
Well, maybe we'll write this first. Tension plus the force of buoyancy is equal to the weight. Weight pulling down, buoyancy pushing it up, and then the tension in our cable holding it up.
Yeah.
And what's buoyancy? There wouldn't be any buoyancy.
The
Because-
buoyancy is always equal to the weight of the water you displaced. And it's pushing up.
But it weighs more.
Right, so buoyancy is not enough to hold it up.
So it doesn't.
So it would sink if we cut the cable.
Yeah.
So it's taking both tension and the force of buoyancy to fight the weight.
Okay. I'll see that. I'm there.
If this were an empty ball, then our tension, the cable, there would be no tension because the force of buoyancy would be pushing it up more than the weight. There'd be no tension in our cable.
Right.
Okay, so tension plus the force of buoyancy. Look, if you were holding a gold statue on the end of a fishing line, is it easier to hold it in the air or when you submerge it in water?
Submerge.
How much easier is it? That's essentially what we're calculating here. Tension is how hard you have to work to hold up the statue. So we would expect it to be a little bit less than the statue's weight.
Yeah, just how much water it places.
So that's what we're calculating. So just really quick, our statue is 15 kilograms, right?
Yeah.
So the weight of our statue
Pretty small statue.
is 15 times 9.8, whatever it comes out to. It's going to be a little bit less than 150, right?
It's 147.
147. So we would expect the tension in this cable to be a little bit less than 147 newtons.
Oh, yeah,
Because it's not quite as hard to hold it up as it was above water.
Yeah.
Okay. So, finding the tension.
Okay.
So move the force of buoyancy to the other side. So tension is equal to
Weight minus.
the weight of the object, which is going to be m, we know. It was given to us somewhere up here.
Minus the volume
Times
of
G.
water it places.
Minus
See,
the weight of the water it displaces.
Yeah. The weight.
Which is going to be, the way we typically do that is we do the volume of the water displaced times the density of the fluid times G.
Okay, but do we know the volume of the statue?
Yeah, so how do we get the volume of the statue? So the volume of the statue, we know its density and we know its mass.
Density.
Oh, okay.
So how do you get mass from volume if you know density?
So you divide by volume, or
You have the mass and you have the density, then it's just volume is equal to.
Mass equals
Density
density
over
times
mass.
volume.
It's density over
Mass equals density times volume. So volume equals
Density over mass.
density over mass or mass over density?
density over
I need to see it written out.
Mass over density. I don't know if you guys have been saying it right. I think you've been saying it wrong. It's mass over density.
Yeah.
Move that to the other side. Density times volume gives you mass.
And we have the mass and we have the density of gold.
So we know rho of gold, and so this will give us the volume of the statue. Good?
Yeah.
So we know what V is. So this will be the rho of water times V. This is salt water, by the way, so it's a little bit denser than regular water. It's 1.03 times 10 to the 3 times G.
Okay.
Yeah, that makes sense.
Everything good?
I would sell water denser than
That, yeah, that's good.
Okay, and now we can calculate all these numbers. We have it all together.
Yeah.
Gosh, yeah, it makes sense.
So we have mg, so 15 times 9.8 minus the force of buoyancy is making it a little bit lighter.
Yeah.
So a row of water, this was salt water, so 1.03 times 10 to the 3 instead of 1 times 10 to the 3
And then what's the volume?
times our volume,
Oh,
which we know our volume is our mass,
Over
15 divided by
19.3 times 10 to the power 3.
19.3 times 10 to the 3. Hopefully I'm not making a parentheses mistake here.
Times G.
Times 9.8. And I get 139 newtons. So the tension is 139 newtons. And so the buoyancy force canceled out about 8 newtons worth of,
Which is very small.
uh,
That's like what,
Wait.
8/10 of a kilogram?
so it didn't make a huge difference. But it's a difference.
If we had like a balloon or something, and we let go, how would we be able to calculate how fast it would rise?
From like what?
From the buoyancy force.
From the buoyancy force.
Up
Yeah.
down.
So the force of buoyancy, it would just give you the net force pushing up on it. You'd have its weight pulling it down and the force of buoyancy pushing up.
So it would just be simple, like one of your regular kinematic equations.
Not kinematic because it's forces, but basic Newton's laws.
Yeah.
Yeah, so if you knew the mass of the object, you know the force on it, you know how it would be accelerating upwards.
Oh, yeah.
Okay, that's cool. I guess you have to ignore drag for that.
Huh?
You would have to ignore drag for that.
Yeah, we'd have to ignore a lot of things, but
Which means that it would be harder to do it accurately in water.
not going to be a great approximation, but it'll probably work for that first instant you let the balloon go. It'd be a pretty good approximation for a split second there.
Or is there that much drag in the air that it would matter for a balloon?
Oh, in the air. I was thinking about wire in the air. I don't know. I don't know. But yeah, you have to push the water aside, which isn't easy.
Yeah.
Okay. Anyways, moving on. So there you go. There's buoyancy force. Next thing we want to talk about now is we're done with static cases, and now we're going to move on to dynamic cases where the water actually moves.
Oh, awesome.
Okay. So we're moving on to fluid flow. We are going to be working with an ideal fluid. What's an ideal fluid? It has no viscosity. It has no internal friction. The water's not sticking to itself. You know, water sticks,
Yes. Yeah.
right? You can fill up a cup of water a bit higher than the brim. You know why you can do that?
It's static, not static. Surface tension.
Surface tension. Where does the surface tension come from?
The polarity of the atom.
Polarity of the molecule composed of atoms. So water is, you know, it's H2O. So it's 2 hydrogens
And one oxygen.
and 1 oxygen. It's a little Mickey Mouse.
You said 2 hydrogens.
Yes.
2 hydrogens and 1 oxygen.
Oh.
Oxygen's much bigger than hydrogen. Hydrogen's your smallest atom. And what happens when they're bonded is they share, the hydrogen shares its electrons with the oxygen atom. Now, terrible lie, but useful approximation. What that means is rather than the electron, or it's one electron orbiting around it, it instead orbits around the whole thing. And this one's one electron orbits around the whole thing. Now, an oxygen atom by itself is neutral. It has 6 protons, 6 electrons. A hydrogen atom by itself is neutral. 1 proton, 1 electron. But when they're combined like this, since that electron is going around, it spends way more time away from the hydrogen atom than it spends by it. And so it's kind of like you just have a proton sitting there and a proton sitting there, which are positively charged.
Right.
And some extra electrons spending some time down there, which creates a net positive charge up here and negative charge down there. And so there's another water molecule right here. That's the exact same thing. It has a negative end and a positive end. Positive attracts negative, and they start hooking together. Da, 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 da.
How high can you get it?
There is a rough idea and some lies about how water sticks. But good enough. So yeah, that creates surface tension, which makes water, you know, kind of stick to itself as it goes past it. We're assuming none of that. So completely viscous fluid, viscosless, no viscosity, 0 viscosity. The superfluid. So we got a superfluid, and we're only assuming steady flow. What's steady flow? Turn on a tap, just a teeny bit, and you watch the water come out. It's all clear. You can see right through it. All the water just moving in a nice, organized way. Now turn on full blast. Suddenly everything looks white. And that's water moving very chaotically as it's going through in its big, giant mess. So nice, steady flow.
This is kind of like laminar flow?
Yes, laminar flow. That's what we're talking about.
If you put a balloon underneath the tap big enough, would it just keep flying up? Like it would in the bottom of the ocean?
Okay.
That's a very complex situation because you have water continually moving down, knocking it down, as it's trying to move up from whatever force is.
Oh.
But, so that's very complex, not something we can answer with just this. All right, so anyways, now we're talking about a fluid moving. So here we go, we got some pipe that I'm gonna pump some water through, and somewhere along the pipe it gets more narrow. With me so far? Okay. Now, if I've got some pipe system, starts out thick and over there it's thin, if I am forcing a kilogram of water through this end of the pipe every second, how fast is water coming out the other end of the pipe?
1,000 kilograms?
A kilogram every second. I can't magically make more water.
Yeah.
However much water is going into the system is how much is coming out of the system if it's completely full of water.
But
Yeah, so it'd be like 1,000.
No.
Because if you do one with
If-
the big end,
If I am pushing 1 liter of water through here every second, then 1 liter of water is coming through here every second.
but it's going.
Because it's the same, it's completely full of water. I can't squish extra liters in there, and I can't make them disappear.
It's just going a lot faster.
So, first thing to notice, I got water flowing through this pipe in this direction. However much water, here's a random cross-sectional area, here's another random cross-sectional area. However much water is going through this cross-sectional area in a second is how much water is going through this cross-sectional area in a second. Or in a millisecond, or in an arbitrarily small dt.
yeah.
You with me?
Yeah.
So, we'll use dm to represent how much mass of water is moving through that cross-sectional area in some infinitesimal dt time. And wherever that dm is, it's the same exact dm over here.
Yeah.
How much mass you move through there is how much mass you move through there. Okay. What is that dm? It's going to be the volume of the portion times the density of the fluid. Volume times density gives you mass. With me?
Yep.
That dV I can express as the area times this thickness. Velocity times time gives you distance. So if the water here is moving with the velocity v1, this distance is v1 times dt.
Yeah.
So that distance times the area gives you your volume. Thickness, area is volume, times, v1, either v, doesn't matter which one, for both scenarios. It works for this scenario and this scenario. So the volume times the velocity times dt gives you your thickness, times A gives you your volume, times rho gives you back your total mass.
Okay.
You follow all that?
Mm-hmm.
Okay. Now, since the total mass here and the total mass here are equal, when I substitute into this for what's here, and when I substitute into this for what's here, those values have to be equal. So the amount of volume going through here times rho has to be equal to the amount of volume through here times rho. Follow that? Now notice what's the same on both sides.
DT, bro.
Yeah, the infinitesimal amount of time that we used is the same in both situations, and the rho is the same in both situations. And so A1 times V1 is equal to A2 times V2.
That's so nice. That's so awesome.
And so the
Is that
area
momentum?
is indirectly proportional to the velocity. If I make my cross-sectional area smaller, the velocity shoots higher. You have great intuition for this if you've ever played with the end of a hose. The water's coming out however fast it's coming out. You cap it some.
Yeah. Good way. Sure.
Make a lot less area, you increase the volume or the velocity a lot.
Yeah.
Make sense? That's all that this is saying. So this is our relationship between area and velocity when we're flowing. One more thing that we want to notice, once again, our arbitrarily small volume, how did we get that? That was the area times the distance the water went.
Volume is area times distance.
Area times distance gives you a volume.
Yeah. Right.
Your area times that thickness, that distance, gives you a volume.
Yeah.
Make sense?
Getting there.
So, this volume, dV, was equal to the area times however far
It's
that is.
in time, okay.
So here's what it is. It's exactly what we did up here. Just wanted to say this as its own separate thing. What does this mean? This means that your change in volume with respect to time is just area times velocity. If you increase the area, then you'll pump more water through every given second. Or if you increase the velocity, you'll increase more water being pumped through every second, if you talk about the water in terms of its volume.
Okay.
That makes sense.
Yeah, it's pretty easy.
Good?
Yeah.
Okay, now let's get to the crazy one.
What?
Bernoulli's equation. And the one that you'll use for pretty much every situation, if you can. Everything else is kind of just a special case of this. So now in Bernoulli's equation, we are going to look at water flowing through a pipe that can potentially change in thickness and can potentially change in height and could potentially change in the water flow speed as it goes. And so we're going to analyze the energy of everything going on now in this pipe.
You have an equation for the kinetic energy of the fluid.
Yeah. 1/2 mv squared.
It's just the same?
It's just the same.
Why?
So we're just going to take what you already know about energy and apply it to this water situation and see what happens. You with me?
Okay.
All right, here's the big derivation and the one that matters the most for everything in this chapter. Here it is, the whole chapter. One derivation. Ready? Break. Okay. So what we are looking at now is we are looking at some portion of water in the pipe, and we're looking at it a split second later. So it's going to move from here to here.
Okay.
As it moves that little bit distance, it moves that much on this end and that much on this end because different thickness of the pipe as we go.
Yep.
We are going to analyze the energy going on. Now, what are we going to keep in mind? A change in work is always equal to the total change in mechanical energy. If you do work on a system, you have to either increase the kinetic or the potential energy.
Yep.
Yeah.
So back to our work energy theorem. So I'm just going to look at the work done on the system. I'm going to look at the change in work, well, the work done, the change in energy, the kinetic energy of the system, the change in kinetic energy, and the change in potential energy. I'm going to look at all these changes as we go from this situation to this situation. With me so far?
Okay.
Now notice as we go from this situation to this situation, the majority of it is identical. Everything that's going on in this middle part we don't really care about. The changes are we lose this little bit and we gain this little bit. As our water moves from here to here.
Yeah.
So we'll just be looking at what was lost here and what was gained here when we look at this difference as the water moves that little bit. Overstressing, or you think you got it?
Okay.
So it's not like what we were doing here, where we said, let's see when it moves here versus let's see when it goes from here to here. We're looking this chunk of water to this chunk of water.
Okay.
So a whole big chunk. And we're going to look at the small change in work, kinetic energy, and potential energy, and put it all together.
Okay.
So let's look at the change in work. What is the work done on the water in going from here to here?
The force over this.
Well, first off, what's causing the water to move? What makes the water move in the pipes? The force from what?
Pressure.
The pressure. So over here we have a force doing work on the water, and it's going to be whatever the pressure is here, P1, times whatever this area here is, P1. Pushing it over that small distance, which I'm going to call ds1.
Oh, pressure is just force within area, right?
Pressure times area gives you a force. It gives you the force due to pressure.
So,
So I was thinking, okay.
So you with me so far?
Yeah.
So that was pushing the water this way. But there's also pressure ahead of it. And so, as it was moving from here to here, the pressure ahead of it was opposing its motion.
So it's like friction.
And so, well, not like friction, like the fact that it's moving to a place where there's still pressure. So, you might think pressure somehow like stored up energy. It didn't use all of its energy suddenly jumping from here to here. It's still at a place where there is still energy. There's still pressure in the system. Water's still flowing.
okay.
Okay.
Or it's going into the atmosphere or whatever.
Or whatever. But the point is, as it's moving forward, since there's pressure ahead of you and the water ahead of you, it's got to push into that pressure.
Mm-hmm.
So the water moving from here to here, we had what's work? Force times distance. So force times distance is doing positive work on the water, since the water's moving that way. And then this force times this distance is doing negative work on it.
Times that distance. Ow, it's not moving backwards.
Because, so the water was right here,
Yeah.
and it moved to right here.
Yeah.
It was moving that way, and the force was that way. This force is doing negative work.
Yeah.
So this is doing negative work, this is doing positive work.
Yeah, I get you.
So what's the change in work? It's the work done by this pressure force minus the work done by this pressure force.
Yeah.
Yes.
You with me?
A lot of stuff that can go out.
Okay, we're going to factor out the P1 and P2.
And then the area times distance is zeroing.
And then notice that the area times the distance here, that volume, whatever that volume is, has to be identical to that volume.
Yeah.
Because however much water moved forward is how much water moved forward. I don't know how else to say it.
It makes sense.
So I'm just going to call that dV.
Okay.
So this A2 times ds2 is exactly equal to A1 times ds1, which is just our small change in volume, or our small movement of the total volume. The volume of water that
Moves.
went from here to there, if you want to think about it as we jumped up and put it there.
Yeah.
Make sense so far?
Yeah.
So there's our change in work. Whew. Now let's find our change in kinetic energy. How do you find your change in kinetic energy? You've done this a million times.
Why not?
You take the kinetic energy at the end minus the kinetic energy at the start. So this is going to be 1/2 our mass, dm, for the mass of whatever portion we moved, which is also going to be the same as the dm for whatever mass we lost here, right? So 1/2 dm times v2 squared minus 1/2 dm times v1 squared. Couldn't be simpler.
That makes sense.
What is mass? It's volume times density.
Yep.
Yeah.
So factor out the 1/2 mass right here, and then you have v2 squared minus v1 squared. Change in kinetic energy. You go with the change in kinetic energy formula?
Change in kinetic energy.
Yeah.
Yeah, it's kinetic initial or final minus kinetic initial.
Right. It's final minus initial, which we can rewrite this way.
Yeah.
That makes sense.
Okay. Now finally our change in potential energy. Because potentially the pipe's going up or it's going down or whatever, changing in height.
Yeah.
So gravitational potential energy. What?
Is there another kind of, it feels like there should be some kind of,
Somehow pressure is a lot like potential energy.
yeah.
Yeah. So there's pressure, which you might think of as somehow the internal potential energy of the system. And then there's gravitational potential energy. Because you can lose your pressure to gravitational potential energy. Okay, so once again, our change in gravitational potential energy, what's that?
MG.
That's your mg y2 minus mg y1.
Did you label your,
Oh, sorry. No, I didn't. So what is y1? It's however high this water is. What is y2? It's however high this water is. Looking at center of mass if you want to think about it that way.
oh, that makes sense.
Okay, yeah, sorry, should have drawn something in there.
Okay.
But I think it all makes sense, right?
Yeah.
Now, once again, what is mass? It's
Sure.
density times volume.
Mhm.
And then we have our g from both of them, and it's just y2 minus y1.
Yeah.
Yep.
Okay, so those are those three things. Now, we have this equation, which relates them. So I'm just plugging into that equation now.
Okay.
Ready?
Yep, let's do it.
All right. So, what was dW?
The,
Change of pressure times dV
Yes.
Yes.
is equal to, change of kinetic energy was 1/2 rho dV times the change in the velocity squared. And the change of potential energy was rho g times the change in height.
Yeah.
Good so far?
Yeah.
And I messed up because I lost my dV there. Sorry.
The DV comes out anyways. Like,
Yeah, now I can cancel out dV, cancel out dV, cancel out dV.
Yeah.
Which is very nice because now we don't have to do any sort of integrating.
That is sweet, actually.
So, P1 minus P2 is equal to 1/2 rho, just distributing it back out,
Yeah.
V2 squared, minus 1/2 rho V1 squared, plus rho GY2 minus rho GY1. Put all your ones with a 1 subscript on the left-hand side, and all your ones with the 2 subscript on the right-hand side. So, rho plus
That's a P.
1/2, thank you, your
P.
P plus 1/2 rho V1 squared plus rho G1 Y1 is equal to second pressure, that. Intuitively was the same. Your pressure plus, this is kind of like almost your kinetic energy.
Is that not your kinetic energy?
It's really close. This is your kinetic energy per unit volume because it's using a mass per unit volume rather than a mass.
Okay.
Which is typically the way we want to think about fluids. We don't want to think about a fluid in terms of how much mass there is. We want to think about it in terms of its density. But it's tracking almost the exact same thing. This is almost an energy equation.
Okay.
So this is somehow like the internal energy per unit volume. This is the kinetic energy per unit volume. This is the potential energy per unit volume at the start and at the end.
And that second pressure, so what are the two pressures saying? So pressure 1.
This P2 is the pressure here. P1 is the pressure here. Which are not necessarily the same thing.
If they were, it'd be in equilibrium, right?
If it were, then these quantities would be the same and these quantities would be the same. Or at least however they were different would perfectly cancel out.
Yeah.
So, I mean, depends, but it's just what it is. Now, the important thing on what this says is that whatever this quantity is at point 1 is what the quantity is at any other point 2. Or in other words, this quantity is a constant. It does not change. Whatever it is at point 1 is what it is at point 2. It doesn't matter where I chose point 1 and point 2 to be. I could pick any two random points in the system and it'd be the same.
Sure.
So it's just like the way that energy is conserved. This quantity is conserved.
Okay.
All right. Now let's notice some things. First off, what do we get if the water is in equilibrium and it's not moving? Then we get P1 plus rho G Y1 is equal to P2 plus rho G Y2.
Oh, yeah.
If there's no velocities, which is exactly what this equation was. So looking at that equation, if you distribute through, you can collect the ones on one side, the twos on one side. It's this exact equation when all your velocities are 0.
That's interesting.
So that was just a special case of Bernoulli's equation. It already captures that.
Why, what did Bernoulli discover this?
I don't know what he personally did relative to this equation. He would have done a huge part. What his derivation would have looked like and how he would have written it, I have no idea.
Is this the equation where we get Bernoulli's principle for?
Yeah, this is the equation. Those other equations are just going to be special cases of this where certain quantities are 0.
Doesn't he say that as the speed of the fluid increases, the pressure decreases?
Yes. So you'll notice that's another thing that this says. Imagine that we don't change the height. So this and this are the same. Those go out. Then if P1 is smaller than P2, V1 has to be bigger than V2 because everything else is the same. And so yes, that is one of the crazy things that this says is that pressure and velocity are inversely related. Intuitively, it seems like the faster the water is moving, the more pressure there would be. But that's just not the case. More speed means less pressure, which seems very strange and very unintuitive. But that is exactly what this equation tells us.
Isn't that how planes fly?
Isn't that what?
How planes fly? How a plane moving works?
Part of it comes from this principle. But another part of it just comes from conservation of momentum. So we'll talk a little bit about wings. And then part of it has to do with just things we're not going to talk about, like vortexes and turbulence. Yeah. Let's go ahead and take a break and then.
I just choose which side to show.
All right. Let's continue now. So we did all the hard part. We did all the math. Pretty much you're just going to have to use this one equation and this one equation for all the problems you solve. And that will be considered overkill. You can use the simpler versions that we came up with, but you can always use those. So let's do some simple problems now, or a couple problems using Bernoulli's equation. So here's our setup. We've got some big, what's it called? Lost the name. Some big tank, some big
Funnel.
silo, is what I was looking for, some silo. some big silo and it's holding a bunch of some fluid in it, whatever the fluid is, with some density rho, whatever it is. Now, the silo is completely open on the bottom, allowing the fluid to escape.
Okay.
Now, it could be a pressurized silo, trying to control how quickly or slowly the liquid escapes from it with the pressure it has here. So our job is to, given that we know that the silo is 12 meters tall, our job is to come up with an equation for how fast the water would be falling out of the hole open at the bottom.
What are you saying with the areas up there?
Now, what we're saying with the areas up here is we are going to assume for this problem that the area 1 is much, much, much bigger than area 2. Even though my picture has them drawn somewhat comparable, it's going to be a giant silo and then something letting it escape very small compared to the silo
You
itself.
mean like way, way smaller.
Way, way smaller, to the point where there's no point comparing the two. In other words, we're going to approximate that something like A2 over A1 is, for all intents and purposes, 0 for our case.
Isn't it the same though? They remove the same amount of water. Or
The area, the area at the top of the silo compared to the area where the water is leaving.
Yeah, but
So where the water is leaving, very small hole, compared to the silo is massive. That's all we're saying.
The water that escapes from the top is the same as it escapes to the bottom.
Yes, the amount of water, but imagine you have a pool full of water, big pool, and it has one of those little drains you can pop open at the end.
Yeah.
The water coming out of the bottom is going to be moving pretty fast. How fast does the water at the top of the pool move down?
Very slowly.
Right. And that's essentially what we're going to be assuming, is that the water moving down is basically 0.
Sweet.
Okay, but so let's set up the situation. So P1, whatever the pressure is inside the silo, plus 1/2 rho V1 squared, plus, just blindly setting up this equation before I even think about it, rho times g times whatever our height is, our starting potential energy. So there's the potential energy at the top, or there's our energy at the top, energy. It has to be equal to P2 plus 1/2 rho V2 squared. And then the potential energy at the bottom we'll say is 0.
Yeah.
Okay.
Right? So we'll call this our 0 spot. So this is H up, this is 0 up. Good so far? And now, since A1 is much bigger than A2, V1 is essentially 0. Because what is V1 related to V2?
It's the same. If
V1 is equal to, looking at this equation, it's equal to A2 over A1 times V2.
Which we're saying is
if
0.
A-
And we're saying A1 is so much bigger than A2 that that ratio is basically 0. And so we're going to be treating this V1 as 0. So in other words, we're going to say P1 plus rho times G times H is equal to P2 plus 1/2 rho times V2 squared. What we're looking for is how fast the water comes out of the bottom of the sink. Right?
We're solving for V2.
Yeah, solving for V2, looking for a formula for V2.
Do we know A1 and A2?
We don't need to.
So here's what we got so far. Just coming with the formula for V2. I'm just going to solve this for V2 now. That's all we're doing. So move the pressure to the other side. So I'm going to have 1/2 rho times V2 squared is equal to P1 minus P2 plus rho times G times H. Good so far? I'm going to multiply everything by 2 and divide everything by rho. So I'm going to get that V2 squared is equal to, I know this is kind of a strange way to write it, but you'll see why in a second. Multiplying this by 2 and dividing this by rho. Trying to make my rho's look not so P-like. And then I also multiply this by 2 and divide it by rho.
2GH, where'd your rho go?
I divided everything by rho. Divide that by rho,
Oh, rho.
divide that by rho, divide that by rho,
Done.
multiply everything by 2.
Sorry.
So why is that strange?
Well, why am I grouping these terms like that is what you might wonder. Now do our final step. So then we get that V2 is equal to the square root
Of all that.
2 times P1 minus P2 over rho plus 2GH. Right?
Yeah.
Now P2 is just going to be the pressure of our atmosphere that we're opened up to. If our tank were open at the top, then P1 would also be the pressure of our atmosphere. And if P1 and P2 are both the pressure of our atmosphere, then P1 minus P2 is 0, and this whole term goes to 0. So if it's not pressurized, then we get that V2 is equal to the square root of 2GH. Where have we seen this before?
It's very familiar.
That is exactly how fast this marker would be falling if I dropped it some distance h.
So it's free fall.
Yes. So notice that if the canister is open, then how much velocity does the water have when it moves down and comes out? As much as it would have gotten by falling down and coming out.
The middle section, not the sides.
Doesn't matter. All that matters is that the hole's 12 meters down. So you could have the silo set up with the hole pointing out the side. Right? If you want to calculate, I've got my pool, and I'm going to have water shooting out, and I want to figure out how fast is the water going to shoot out. It's identical math to what we have here. It's the exact same scenario.
So not very fast.
It would be moving out exactly as fast as that would be falling when it hit the ground.
So not fast.
Well,
Let's
I don't
see
know
what
what
that
fast or
is.
slow is.
Well, I expected that to be way faster because there's a ton of pressure on the top. 'Cause there's no-
Well, you've seen water come out of these things. It's not like it's shooting fast.
Fair enough.
Now, of course, this is with an ideal water, which our water isn't. It's viscous and it has all the problems it has, but it would be a decent approximation for a big enough hole. The smaller the hole is, the worse our approximations are. Hard to get water, because of its surface tension, to go through small holes.
Fast.
And that's why you want to clean with hot water, because the water's bouncing around more, less surface tension, easier to squeeze into small holes.
Is that real?
Yes.
I thought it killed germs better.
Well, it's also moving around and it can help disturb whatever there is. But large part of it is simply it gets into smaller holes easier. Okay, so there we go, calculating exactly what we might have guessed going into this. If I took a ball of water and I dropped it and it went all the way down and out the hole, we'd expect the kinetic energy to be equal to however much potential energy it had falling through the system.
What about any vector force from the sides of it trying to go down? Because the water falling down will push against the water coming straight down. Doesn't that create some sort of...
No, we're going to have what we call steady flow. There's not going to be any vortexes. We're not going to be creating any whirlpools. No side-to-side motion. Everything's just nice, steady drain.
It's, yeah, nice, but the ones going on the side are going to be pushing down like that, right?
Everything's going down at the same speed. Nice and steady.
The pressure will still apply to the drain.
It's
Yeah, but... the
going through
speed-
equilibrium fast enough with how fast we're draining it that it's completely insignificant.
It's not real.
Okay.
It still seems like it would be a big enough factor.
Well, it would be if we suddenly tried to drop out almost the entire bottom and watched it fall. Then you'd get like a whirlpool effect.
Yeah.
No,
When
that's-
it's draining really fast relative to how much water is there, then that starts mattering more and more. The slower it drains relative to how much water is there, the less that matters.
Okay.
Okay, anyways, let's talk about two ideas really quick. First off now, that we talked about all this, let's talk about how we actually measure now the pressure of the atmosphere. I said, here's the pressure of the atmosphere. How on earth do we know the pressure of the atmosphere?
Relative to vacuum?
How do we measure it? Here's exactly how we measure it.
In units of mercury.
Yeah, we typically use mercury. Why do we use mercury?
Because
It's
a metal.
really, really dense. And it's a liquid
Really
at room
dense.
temperature. Yes. Mercury is roughly 13 times as dense as water. Almost 14 times as dense as water. It's very heavy.
So why can't water... Okay.
So we could build one of these meters using water. We typically use mercury. Okay, so how does it work? You take a big glass tube and you basically vacuum out one end of it so that there is zero pressure there. You have that big glass tube in a pool of mercury. So the atmosphere, the pressure of the atmosphere out here is pressing down on it with the pressure of the atmosphere. And now, when you look at a point right here, whatever P is right there, pressure there has to be exactly equal to whatever the pressure is there. And the pressure here is dictated by how much is on top of it. And so the pressure of how much on top of it is just rho GH. So rho GH gives me the pressure here, but that's also equal to the pressure of the atmosphere. And so you can literally just see how high up the mercury is, and that tells you the pressure of your atmosphere.
Why does it have to be mercury?
It doesn't. But with mercury, when it's at 76 centimeters will balance out the atmosphere. If we use something like water, we need over 10 meters. I don't want a glass tube 10 meters tall if I can use one that's just 76 centimeters tall.
And mercury is the densest thing for this?
Mercury is a very dense liquid. You want it to be a liquid.
Yeah. Okay.
At room temperature. We don't want to have to keep, gold hot the whole time so it can function as a liquid to do this.
Wow, that would work though.
Is gold more dense?
Yeah, you could use other materials. We use mercury because it's a very convenient material. It's liquid at room temperature, it's dense. It's also why you use it in like thermometers. We'll get to thermometers when we get there, but guess we should have already talked about them. Doesn't matter. We'll stick with this. Okay, so there you go. And that's how you can measure atmospheric pressure. And so as it changes, when a storm's coming in or whatever, I don't know what it's supposed to be as the storm comes in. I think pressure is supposed to drop a little bit. One of the ways that they are able to predict what the weather is going to do, measure the atmospheric pressure.
Do they really still use mercury barometers for it?
I doubt that this is the way that, well, I would guess to some I don't know. Here's the way it was initially done. There's the physics behind it. I'm sure that they have clever ways of manipulating the physics now, but I have no idea. Okay, let's talk about another scenario. Here I've got some crazy container.
Okay.
Open there, open there, open there.
Okay.
I'm going to fill it up with water until the water comes up to right here in this pipe. Question, how full would the water be in this pipe?
Like halfway then?
Down by half.
Like right here?
Yeah.
Sure.
So you're thinking it would be about that high there, and what about over here?
Or pretty low.
1 inch off.
Like
I
just
don't know.
barely like that?
Yeah, that seems about right.
So this whole thing is filled up with water.
Wait, what?
So I'm pouring water in,
No, I'm tripping. This should be all the same, shouldn't it?
all the same.
I
No. No, this should all be the
Oh no. Wait.
Should they all be the same height? Should they all be different heights?
Yeah.
What should be going on here?
That's right.
Well,
Our hydraulics are all the same, right?
pressure applied to an enclosed fluid is transmitted to every portion of the fluid and the containing walls undiminished. So the pressure here is going to be the same as the pressure here is going to be the same as the pressure here. So the amount of water above this has to be the same as the amount of water above this has to be the same as the amount of water above this. So it's going to be the exact same all the way across.
No, you're saying volume, right?
I'm saying how much water, what would the water level be in all these things
Yeah,
as
so
we're
it's all
filling
the
it
same.
up with water.
That makes sense. That's reasonable.
And it will be the same all the way across.
I can believe that.
Oh, I didn't realize that was your question. Oh, yeah.
Give you,
Very obvious when you think about it.
Yeah. Makes sense. It would balance out.
Yeah.
trying to draw something somewhat similar to what you see right there.
Okay.
And so all the different openings, it all levels out.
Yeah.
Okay, that's what we're seeing. Nothing fancy, nothing special. With me so far?
Yeah.
Now think about why this is kind of weird.
It is a little weird, yeah.
Why would the pressure here not be higher than the pressure, I don't know, like right here? It seems like some of the way the water is being captured by the container.
Well, because it doesn't, because it's perpendicular and then also distributes out among the entire fluid.
Well, according to the Archimedes principle, the pressure is the same here, here, and there. All the same.
Yeah, distributes out.
And somewhere in the middle, also the same. Somewhere in the middle, also the same.
That's not Archimedes, that's Pascal, is it?
Oh, sorry, thank you. You are correct. I was saying it wrong. Okay. So now we got that. Now here comes a real tricky question. Here I am inside of a giant pool, completely full of water, feeling the pressure down here. All right? And I feel whatever pressure, we'll call this pressure P1. That's a lot. Here I am in a pool, half is full.
So you feel half pressure.
And so we call that pressure P2. We would expect that to be about half the P1. Now I take this pool, and I just cap it off, and then I put this little tube that goes up, barely a centimeter thick, all the way up, and I fill that up with water. What is the pressure in here?
Same as P2.
Is it going to be the same as P2, or is it going to be the same as P1?
P2 with a little extra.
There's absolutely no way it's the same if you want.
It's not.
And the answer is it's the same as P1.
That's insane.
It's exactly what's going on in this scenario when you consider what's going on over here versus what's going on over here.
So you're telling me that the person at the bottom of the third tank is
The person in here is feeling as much pressure as a person in here if this is the same height as that.
What the hell?
Very unintuitive.
Does it have anything to do with gravity?
And so, it's not really a question of how much water is above you. It's a question of how deep the water is above you.
Why? Is it gravity?
Very unintuitive.
There's
It's
no-
just what it's a consequence of.
That's the what?
That's a.
So if I were standing in just a little container that went all the way up to the top of our atmosphere and felt all the air in there, and I suddenly break those walls and let all the atmosphere from everywhere flow, it doesn't make a difference. It doesn't matter how big the sea of atmosphere is I'm in. All that matters is the depth of the atmosphere I'm in.
If someone took a huge straw and put it in like a bathtub like that, then the guy in the bathtub would die because of the pressure.
Well, no, notice how this is contained, so the fluid's all the way full up like that.
Well, yeah, I'm saying.
Oh, that makes so much more sense.
What is?
If I put you inside of a bathtub, completely sealed, completely full of water, all the way up now with a tall hose, really tall, then yes, that's going to increase the pressure that you're experiencing.
Why?
By a lot. Or some sort of pipe that we have running out.
That is interesting.
It's very unintuitive. What is a consequence of something like this? If I build some big strong dam, here is my big strong dam, and it's holding back some big lake, that dam is doing as much work as if it were just holding back this little bit of water right here.
You showed us this last year.
Same pressure.
You showed us. I remember this.
Roughly what it is, because we've been dealing with idealized situations up to here, but it's roughly the first inch is all that matters.
First inch.
First inch is all that matters. Because that produces the pressure. The pressure is what the dam has to be able to withstand. The dam doesn't know if it's holding back a little bit of water or if it's hooked up to an ocean.
I guess.
When you go to the edge of the sea and you stick your hand in the water, you'll say, oh, that's hard. I'm holding back the whole ocean. But when you do it to a little pull, say, oh, that's easy. It's just a pull I'm holding back. The pressure is the same. It's just related to the depth.
That's
It is not related to the volume.
What the heck?
Very unintuitive.
Why does the inch matter? Like, what line is that drawn?
It doesn't matter. The point is, a small amount and a large amount, the dam doesn't know the difference. That's what matters.
But we don't have the numbers.
There are numbers, but the point is, we don't care. The principle is telling us that small versus a lot, it doesn't matter. This and this are the same.
Yeah. Okay.
That's what matters. Very unintuitive. Okay, so now with that, let's do our last example problem. Here we got, oh, can't remember what these things are called, but basically a way of measuring water pressure, or measuring the speed of water. So here I got some pipe, water flowing in the pipe heading that way. The pipe becomes more narrow as it goes. If it's becoming more narrow as it goes, we expect the speed to increase. It has to increase if it's becoming more narrow. Now, in the big pipe, somewhere along it, doesn't matter where I have it stuck, I insert a pipe that goes all the way up to the atmosphere. So up here we have a pressure of 1 atmosphere. Pressure of the atmosphere in that open pipe, also in this open pipe. This pipe's open to the big one, this one's open to the little one. Question. Is the water in this pipe going to be higher, lower, or the same level as the water in this pipe?
Same. It's the same. But you're-
Same. Of course it's the same.
Okay.
Okay, and the answer is lower.
Of course.
Oh wait, there's less pressure. The water moving faster.
Oh.
Which is going to have a difference of h.
Sure.
And yes, why is this going to happen? Again, unintuitive.
Damn.
We're going to see, as the water goes through this pipe, I tried to draw it in such a way that the water is not moving up or down. The center of mass of the water is staying the same.
Yeah.
And so, if the velocity is increasing, going from here to here, the pressure has to decrease. So says Bernoulli's equation.
Yeah.
So writing out Bernoulli's equation for this situation, we'll call whatever height the water's at, height 0. Then I now know that P1 plus 1/2 rho times V1 squared is equal to no potential energy since it's staying at the same height. is equal to P2 plus 1/2 rho V2 squared. Right? That's what Bernoulli's equation tells us. If V2 is bigger than V1, P2 has to be smaller than P1 in order for it to be a true equation. That's the only way for it to work. And so the pressure here will have to be different. And so if the pressure is different here than it is here, it's going to push it up a different height because that's just directly proportional to the pressure.
Right.
You with me?
Yeah.
And now, that's the important part of the problem, the reason I want to do it. The problem tells us to solve for V1 in terms of A1, A2, and H, so we'll do that, but that's the reason I wanted to make sure we did this problem. Very unintuitive result. Okay, so now let's just finish the problem. So let's see, I'm solving for V1, so I'll keep this on this side, put the P1 over there. So I get 1/2 rho times V1 squared. Oh, actually, I'm going to put my pressures on the same side and my velocities on the same side. So I'll put my pressures over here, velocities over there. So I'm going to get P1 minus P2 is equal to 1/2 rho. We're moving them over here, so this one's my positive term. V2 squared minus 1/2 rho V1 squared. Everything good so far? Now, our change in pressure is always proportional to what?
Change in pressure is proportional to area, no, mass or velocity, or
Going all the way back to wherever we have the equation. Change in pressure is just equal to rho GH.
Yeah.
So, this change in pressure is going to be the same thing as rho GH. Whatever the change in pressure is between this point and this point is just going to be rho GH for that H.
rho GH.
Yeah.
Why
So
do
rho times G times H is our change in pressure from P1 to P2.
Okay.
It's going to be however much that change is. That's going to be our change in pressure. Okay, so this is going to be equal to, I need to solve for V1, so I'm going to have to substitute out V2. How can I write V2 in terms of V1? Here's something you're going to have to do a bunch of times. Perfect. That equation right there. So V2 is equal to what?
A times B divided by A.
Which A?
Or A1 times V1 divided by A2.
A1 over A2 times V1, right?
Yeah.
Okay, so that's the substitution that I'm now going to make for V2 here. I'm going to factor out the 1/2 rho from both of them.
Okay.
So here's my 1/2 rho. And then for V2, it's going to be V2 squared. So it's going to be A1 squared over A2 squared times V1 squared. Everything there good?
Yeah.
And then that's going to be minus V1 squared. Good? I can divide out the rho on both sides. That'll get rid of that. I'm going to multiply the 2 over here.
Yeah.
I'm going to factor the V1 squared out. What's remaining over here? So 2GH, put the 2 over here, is equal to, over here, factor out the V1 squared. So it's going to be V1 squared times A1 over A2 squared minus 1. Move this to the denominator over there and square root both sides. And we're going to get V1 is equal to
Square root 2GH
of
over A1 over A2, or A1 squared, A2 squared.
squared
Minus 1.
minus 1. Okay, that's what it's going to be.
That's,
And that you just use those two form. Oh, you use that one over there too.
yeah.
Shoot.
And so,
This is hard.
they often have systems set up like this into their plumbing and calculate the difference in the height to calculate how fast the water is moving through whatever the pipe is. So it goes thick, they have a part where it goes thin for a second and then back to thick for the rest of it, and it tells them how fast it's going through the thick part.
That's interesting. That's actually so smart.
Okay, so with that, let's fix my hair real quick.
Fix your hair.
Now I'll do a demo. Let's talk about the demo first. So I'm going to take that ping pong ball. Well, first off, let's think about, you can think about the air now kind of like a fluid. right? If I were to take like a hose and spray it onto a ping pong ball, how hard would it be to hold the ping pong ball up straight in the air with a hose spraying it?
Not easy.
Not hard at all.
Not hard at all? Almost impossible. It's just gonna whack that ping pong ball somewhere crazy.
Oh, water.
Water.
Yeah, if I take water and I spray my ping pong ball, trying to spray it and hold it up in the air, it's gonna be really hard to hold it in one position. All that water just whacking against it is just gonna knock the ping pong ball off somewhere. Okay, so now let's try something here. I'm gonna take my ping pong ball and I'm gonna blow it up. And it should just go flying. Hold on, we can do better. And you'll notice, if I could do it well, let me set down my marker. I am not good. Let me get it a little softer. I did it at home first. All right, one of you come help me.
Do I need to drop the ball?
Did I get it? I just also need to try and keep that. Okay, there we go. So you notice it's holding it actually pretty stable.
Yeah.
And you can go ahead and poke it gently. Don't whack it too hard, but
Poke it out or
just poke it. Like it's not super easy to disturb it. It will fall back into place pretty easily.
yeah.
Very strange, very unintuitive. All right. So the question is, why on earth is that happening? Why isn't it just knocking the ping pong ball away? Why is it that I can get some stable configuration there?
It's the ping pong. I don't know.
The air blowing up, it creates a circle on top of the ball and the ball stays.
There's lower pressure underneath the moving air, maybe, and then the higher pressure from the atmosphere.
Yeah, so you have your ball here, and what you have is as I'm blowing the air is coming up around the ball, up around the ball, up around the ball like that, right? And so the air here is moving very fast compared to the air over here isn't moving much at all. What is that doing? That's making low pressure here and here with higher pressure here and here because the air is moving faster and velocity means lower pressure. And so the ball moves from the high pressure areas back to the low pressure areas over and over again. And it actually creates a pretty stable configuration.
That's pretty cool.
With a little bit of practice, you can make it work every time. It's good to practice more, but we're seeing once. All right, let's look at something else again. Here's a ping pong ball sitting here. Nothing fancy about the ping pong ball, just blowing the ping pong ball. Little bit of blowing knocks it very easily. So what we're going to try to do, I'm going to put this ping pong ball in here. I want you to guess how high I can get this ball to go. I'm going to blow in it. I promise I'll blow as hard as I can, trying to blow it up as high as I can get it. Do you think I can get roughly to the ceiling, roughly top of the board? What's your approximation on how high I can get this?
6 inches.
12 inches.
Fair warning, I do have asthma, so
12 inches.
Not
the strongest lungs in the world,
Not very far.
but you'll see how high it pops. Can't even get out of it. And you can go get a funnel and a ping pong ball at home, and you can blow to your little heart's content. It's not going to go anywhere. There's nothing fancy going on here. It's not sticking in there. This isn't a magic trick.
It just rolls.
It's just basic physics. Now, shockingly, when you blow onto the floor, you can get to really pop.
Oh.
Once again,
That's
I'm blowing down on that ping pong ball, and it refuses to leave my funnel.
that's cool.
That's
I bet you the pressure from the air is
What on earth is going on there?
the velocity is so high that the pressure is low enough where the pressure from the atmosphere keeps it in the funnel.
So you got your funnel,
Oh, it
and you got your ping pong ball. What's happening is, as I blow air through,
The pressure lowers.
Velocity is so fast.
the pressure here and here is very low. Compared to the pressure up here is high. This is high pressure, that's low pressure. The pressure pushes the ball towards the low pressure. And so I can't blow that ping pong ball out. The atmosphere is shoving it right back in my face. Even if I try to blow it down, get gravity to help me. It refuses to.
Is there less pressure outside, or higher we go then?
There's less pressure the higher we go, just due to the thickness of the atmosphere. The point we're exaggerating here is that the faster the fluid moves, the lower its pressure. And so that's what's holding the ping pong ball up, even when I tip it upside down. I'm blowing down on it.
How does velocity tie with pressure? Like what?
With Bernoulli's equation. Look, in this scenario,
Okay.
using Bernoulli's equation, this pressure plus this velocity was equal to this pressure plus this velocity. If this velocity goes up and it's equal, this pressure has to go down.
That's right.
So as the velocity goes up, the pressure goes down. That's what we're showing here. Just increasing the velocity decreases the pressure. And then trying to show it with you. Now understand, with air, this is not an ideal fluid. Air is compressible for one thing, but it gets you the idea. And it still is a good approximation for what we were doing with the ping pong ball. And so it still holds.
Spinning.
So spinning ball, now let's talk about just a spinning ball. How does a spin work when you, I don't know, you play baseball, you put a spin on the ball.
Magnus effect?
Ping pong, ball, you whack it and you get a spin on it and the ball moves.
Yeah, Magnus.
It's because of the same effect. What's happening? So here's my ball, and we'll say that it's spinning this way, as it's flying through the air that way.
Okay.
So the ball's flying through the air that way, spinning like this. Which way is a spin going to cause it to move? You have intuition for this. When you hit a spin, the ball moves in the direction you spin it. So if this is a bird's eye view looking at a ball flying this way, but it's spinning like that, it's going to move this way. Now, why does it move that way? So, relative to the ball, here's the air flying past, right? And the ball's spinning. This part of the ball creates drag on the air as it moves past, slowing it down. As it spins down here, notice the air is moving that way and it's spinning this way. It's also pushing the air that way, speeding it up. So the air down here is moving faster than the air up here.
Really?
And lower velocity means higher pressure. So the pressure is higher up here than it is down here. And so the ball goes da-da-da-da-da on its merry way.
Curves.
And it curves. So it's moving straight this way because that's where you threw it. And it's moving this way because you spun it.
What about the other way? If you hit it the other way.
What do you mean?
So turn your arrow the other way.
Well, then it's
If you spun it this way, then it moved that way.
So it can fly.
no, this is a bird's eye view.
Bird's eye view looking down at a ball.
Horizontal.
Oh.
So you whack the ball, it's flying through the air.
Gravity affects it inside.
The ball's flying this way, but you put a spin on it. So it's also going to move this way.
So
if you spun it.
If you hit it hard enough, though, downwards, it's going to fly.
You can give it a spin to try and make it go up. In sports, they often do what they call a backspin to make it drop. A top spin to make it drop.
Somebody made a.
I know what I'm doing on top spin.
Popper buckets that would fly by spinning.
Okay, let's talk a little bit now about plane wing. What makes planes fly? Well, lots of things. We'll talk about a piece of what makes a plane fly.
Everybody likes to argue
I
about
just
this.
did this.
Huh?
Everybody likes to argue about this one.
Well, they can argue about it. Okay, plane wing. It's going to be in kind of a teardrop shape, something like that. I'm not an artist, but it's going to be something like that. One, it's going to be tilted up, and the plane flies this way. So part of what keeps the plane up is just flying through the air, pounding into the air molecules, pounding against the bottom of the wing, knocking them down. If you change a momentum, you must have a
Change in momentum.
change in momentum gives you a force. Force is a derivative of momentum with respect to time.
Yeah.
So that produces an upward force. Okay, there's a bunch of it. What else is going on with the geometry of the wing? With the geometry of the wing, it is creating a pressure difference. It's compacting, because not an ideal fluid, but it's compacting a bunch of the air up here on the wing, pressing it together, creating a high pressure situation. And it's kind of blocking some air from getting down here where there's a more low pressure situation. And so, the speed of the air going over the top of the wing is much faster meaning it will get to the end here faster than the air going this way by about 20% quicker. So if you were to watch some sort of wind tunnel situation where they throw like chalk in there or something that you can see, you're going to see what goes over the top goes faster than what goes over the bottom.
The top of the airfoil is also a bigger distance, isn't it?
The top is also a bigger distance, but in particular, the air moving over the top is traveling faster than the air moving under the bottom. And so there's a pressure difference there, which means that there's an upward push. So that's part of what goes into an airplane's wing.
Sick.
Now, you can't just apply Bernoulli's equations because we're not even talking about close to an ideal fluid.
Does this still apply in supersonic flow? Do the same kind of principles apply there? Do you know?
I have no idea, because that's going to get complex. Okay, let's do one more thing now. Now I'm going to try and confuse you by something that confused me back when I took this for the first time.
Okay.
I need one of you to be my cameraman, because we're going to have to do this over the sink. So, get the camera, come over here, and we'll do our quick little demo. Something you've likely seen 100 times before. But now that you know everything, you'll know enough to be confused by it. So, here I am, I've got some water. And all we got is cardboard. Usually helps to wet the rim a little bit to stop air from getting in or out. What is the pressure inside of the air inside of here?
Oh, it's just 1 atmosphere.
1 atmosphere. Now what is it?
It's also just.
It's still just 1 atmosphere, right?
Yeah.
So, what is the pressure difference between inside and outside? The pressure out here is 1 atmosphere. The pressure in here is 1 atmosphere.
Wait, what did you just do?
That's just cardboard resting on it, holding up the water. I'm not doing anything. This isn't a magic trick. This is just physics. Now, how does this make any sense?
Suction.
1 atmosphere of pressure inside the cup, 1 atmosphere of pressure outside the cup. There is no pressure difference. Now, this was something before a kid would just say, oh yeah, suction, and go on their merry way, thinking that somehow there's a vacuum, and vacuums just suck up things. What on earth is going on with this?
Can the
Why is it holding it up?
Well, if the water tries to leave, then the air inside would be less than 1 atmosphere, wouldn't it?
If the water gets out, now it is leaking a little bit, so unfortunately, but what's going on there? So I'll leave that one for you guys to think about.
How did you do that
And let
to
it-
begin with?
All right, this is very tricky. First, you have to put water in the cup.
What?
Then you have to put the cardboard over the hole of the cup. Then you got to tip it over, let it settle some so that it's a somewhat stable system, and then you let go.
So if I did that with a plate at home
It
and
would work, yeah.
a glass, then it would work.
Wow. Oh.
Don't break your plate.
It's holding up only so much weight, so the more weight I put there, the less stable it's going to be. I mean, if I push down on this a little bit, there it goes.
Very interesting.
Yeah, so there we go. That's our last demo, and that's it for today's lecture. You can go ahead and pause that now.